Welcome to yet another class. I'm Dr. B, your chemistry teacher. Today, we are going to look at something concerning standard free energy and the standard electrode potential. Very important. This is an aspect in electrochemistry. But before we continue, please remember to share this class. Remember to share this class. And when you share this class, don't forget to let them know that they should do a subscribe so that they can be able to follow, get these videos as soon as they come. Okay, and then we also have a Facebook page, and that is Dr. B Chemistry Classes or Dr. B Science Classes. They all need to follow. Once you go there, please share and instruct them to follow so they can always be getting these videos as they come. Thank you. Now, we are going to look at the standard free energy changes from the standard electrode potential. How do we obtain standard free energy from standard electrode potential? We can always obtain the standard free energy from different aspects in electrochemistry, but we can also obtain standard free energy from the standard electrode potential. But the standard free energy, of what relevance is it? Remember that standard free energy helps to tell you so much about the chemical reaction. It is one particular thermodynamic parameter that is used to determine feasibility of a reaction. So for you to be able to tell whether a reaction is going to be feasible or not, or a reaction is spontaneous or not, it is the standard free energy change that would be able to tell you if that reaction will be feasible or not, if that reaction will be spontaneous or non-spontaneous, because this particular function or parameter of the of thermodynamics is not specific, so it can tell you so much about a chemical reaction in the system. Again, the standard free energy can also assist to tell you about the type of reaction, whether a reaction is physically absorbed or is physically absorbed and physical mechanism, or is a chemical mechanism. It can tell you that. It can also tell you about the stability of the reaction. So the standard free energy goes a long way to explain a lot of things. But what is the standard electrode potential that we are talking about here? Okay, the standard electrode potential is simply explained in this way. So I put it in a way you will just understand. Now, you know that we have chemical reactions, especially in electrochemistry, we have chemical reactions that take place in the electrolytical cell. And in that electrolytical cell is a chemical reaction that is happening there. Now, if you want to measure the potential of a reaction, okay, around the electrodes, as far as all the materials that you use in that reaction are all in their standard state, then that potential you'll be measuring around that reaction at that electrode will be simply described as a standard electrode potential. Okay, so the standard electrode potential, simply put, is simply the potential of a reaction, or the measure of the potential of a reaction around the electrode, where all the materials that are used in that reaction are all in their standard state. And when we say in their standard state, we are saying, for example, the solution that you use in preparing that reaction, or for that reaction, is 1 molar. If it's a gas, for example, the gas is in 1 atmospheric pressure. If it's a solid or it's a liquid, it means that they are in their pure state. And all these particular materials that are used in that reaction must be all in 25 degrees Celsius. That is at ambient temperature. So that is what we understand by the standard electrode potential. But our problem here today is how we can be able to calculate the standard free energy change from the standard electrode potential. Now, a question is given to us here, and the question says, calculate the standard free energy change at 25 degrees Celsius, which of course it shows that the solids and liquids that are used in the process are all at standard state, using standard electrode potential. And you are given an equation here. This is zinc reacting with silver in solid form and aqueous form. I'll give you zinc, aqueous, and silver in the solid form. And these are their electrode potentials, standard electrode potentials with the 0 on top. So the standard electrode potential for zinc is 0.76 volts, and that for silver is 0.80 volts. How do we now calculate the standard free energy out of these standard electrode potentials that are given to us. The first thing we must understand is that we need to understand the equation that is given to us. Usually, standard electrode potentials or standard electrode potentials, of course, of certain reactions are always electrolytical. And if they are electrolytical, then they are oxidation reduction equations. The equation that is given to you here is an oxidation reduction equation. You can call it a redox equation. So if it's a redox equation, you have to first start by doing what? Understanding which part of this reaction is oxidized and which part is reduced. That's the first thing you must know if you are given standard electrode potentials for you to calculate standard free energy. You must understand which part of the equation is an oxidation equation and which one is a reduction equation. There are different ways we define oxidation and we define reduction. Some people define oxidation by the basis of what? Addition of oxygen and removal of hydrogen. Some define oxidation and reduction on the basis of their charges, okay, the charges that they carry. Some define them on the basis of what? The electrons that they carry and all those kind of things. Now, if you look at this equation, we will only be able to define the oxidation and reduction equations on the basis of the charges that they carry. Where you have increase of charges, it is what? Oxidation. Where you have reduction in charges, is what? Reduction. And if you take a look at this equation, this is zinc. At this point, zinc is at standard state and this is 0. Alright, this is 0. If you take a look at the zinc at this point, there is 2 plus at this point here. There is 2 plus. That means there is an increased charge in zinc from the reactant to the product. So at the product, zinc is increased in charges plus 2. So it is very simple for us to know that zinc in this equation is oxidized. And the silver is still silver. It is 0. It is having a charge of plus 1, okay, in this equation. Now you will see that this charge of plus 1 is lost at this point. So it is at a standard state at this point. So silver have lost this charge of plus 1 to become reduced. So zinc has an increase in charge at the product, so zinc is oxidized. Silver has a reduction of what? Charge at the end, at the product, so it is what? Reduced. Therefore, zinc is oxidized and silver is what? Is reduced. And of course, you know that because zinc is oxidized, it is what? A reducing agent. And because silver is what? Is reduced, silver is what? An oxidizing agent. Do not confuse yourself. Alright, now let us solve this problem. Now let us write out the half cell equation. Because we must write out the half cell equation before we be able to solve the problem. To write out the half cell equation, we have to write the oxidation equation, the reduction equation, and the overall equation. Now let us write the oxidation equation, knowing now that we know that zinc is what? Is oxidized. So the oxidation equation would be zinc solid, okay, oxidizing to lose what? To lose to gain 2 electrons. Plus what? Plus zinc 2 plus. Okay, that's what we have. So the zinc 2 plus is aqueous. Okay. And then the reduction equation is the silver. So silver plus aqueous. Okay. Plus what? 2 electrons that are lost, and this will give us from here to here. This will give us 2 silver solid. Now we have that. Don't forget that the electrode potential for zinc is minus E0 equal to 0.76 volts, and this is minus E0 for silver, 0.80 volts. Okay, now with this we can be able to write the overall equation. We have written the oxidation equation for what? For zinc. We have written the reduction equation for silver. We now need to write the overall equation. To write the overall equation, this electron will cancel this electron. Alright, so we'll cancel it. Now, if we get this, then we mean I'll have zinc as solid. plus 2 silver as aqueous, that is this, giving us this zinc as aqueous 2 plus, okay, plus silver, 2 silver as solid. So that is the overall equation. Now, with this overall equation, we can have the summation of the potentials to give us the overall potential. So if we add 0.76 plus 0.80, what are we going to have? We are going to have the electrode potential for overall become 1.56 volts. Of course, that's what we have. So if we add the potentials that we have here, we'll have 1.56 volts. Because 6 plus 0 is 6 and 7 plus 8 is 15. So that is 1.56 volts. Alright, now we have been able to get the oxidation reaction, the half cell equation for the oxidation, for the reduction, and the total overall equation for this particular reaction. We will now do what? Calculate the what? The standard free energy. We will now calculate the standard free energy change. Without you being able to get this, you will not be able to calculate the standard free energy change. So we now calculate standard free energy change. And what is the actual formula in calculating standard free energy change? I'm sure you know it already. Let us write it together. Alright, now to calculate the standard free energy change is always given as NF is that. That is the equation for the standard free energy change. The N, the F, and the E. Of course, the N is the number of electrons in the reaction, and then the F is the Faraday constant, while the EO is the standard what? Electrode potential. Alright, that is why we needed the overall standard electrode potential, which is this. So all that we're doing here is for us to get this, which is the overall standard electrode potential. So, with this, we can simply substitute. The number of electrons here is 2. Look at them. So, it's 2 electrons. The Faraday constant is 9.65 times 10 raised to the power 4 coulombs times our what? Our overall standard electrode potential. And this is 1.56 volts. So this is 1.56 volts. It's as simple as that. And with this, I want you to use your calculator to do this. Let's see. If you multiply 2 by 9.65 times 10 to the power 4 coulombs times 1.656, you should be able to get something like minus 3.01. Okay? Times 10 raised to the power 5. That's what you have, and this will be in joules. It will be in joules because coulomb times volt is in joules. Coulombs times volt is joules. So in as much as we are multiplying, this is neutral, so multiplying coulombs by volt, the answer will be what? In joules. And if you convert this into kilojoule, you have 301 kilojoules. So your standard free energy change is, here is what? 301 kilojoule, or 3.01 times 10 raised to the power 5 joules. So this is just the simplest way you can be able to calculate your standard free energy change. Ordinarily, they will have just been what we are going to be basing on. But we need to understand the oxidation reaction, the reduction equation, and understand the redox equation as a whole to be able to determine the total what? The total electrode potential equation, or the total redox equation, where we can be able to determine what we call the overall standard electrode potential for the overall equation. Then we can now use that to fit into the Gibbs free energy equation, which is this, for us to be able to calculate the Gibbs free energy. So this is a simplest way, or you can always calculate Gibbs free energy changes from the standard electrode potential. I'm sure you have learned something out of here today. Do not forget to share, do not forget to like, to comment, do not forget to also follow my Facebook page, and please subscribe. Tell those you ask, you share these classes with, to do what, to subscribe, to be able to get this information as soon as they do what, they drop. Until next time, I'm still Dr. Ben, I'm still Dr. B. It is